Okay, so that short generalization, all we did was just generalize the what we did in the one-dimensional case. Okay, this is the one-dimensional Schrodinger equation, and we just generalized this basically by replacing the potential with something which can depend on x, y, and z, and generalizing the kinetic energy term here to include derivatives in the different spatial directions, and that basically gives us, in a simple, straightforward way, the three-dimensional Schrodinger equation. So just like we did in the one-dimensional case, we can also separate the time and space components of psi. Okay, so we can write psi as a product of a function that depends only on spatial coordinates, and a function which depends only on time. So psi of x, y, and z, and phi of t. Okay, and so this basically can apply when the potential energy is time independent. Okay, and so then when we do that, we can write the time independent Schrodinger equation in 3 dimensions, which we have right here. Minus h bar squared over 2m times del squared psi plus u of times psi is equal to E, which is just a number, the total energy times psi. And again, this left-hand side is basically the Hamiltonian operator, three-dimensional Hamiltonian operator acting on psi. Okay. In one dimension we saw that the boundary conditions give rise to a quantum number. Okay, like for example in the infinite square well, we found that the energies were proportional to n squared, where n is an integer no smaller than 1, and so the energies in the quantized energies in the infinite square well increased with in this way proportional to n squared. In the harmonic oscillator, we saw that it was linearly proportional to n, so the spacing between energy levels was uniform, but nevertheless you can the eigenenergies, the values for the possible values for the energy solutions, for the energies of the eigensolutions, the eigenfunctions, were described by a single quantum number. In 3 dimensions, we have to apply boundary conditions in all three spatial directions. Okay, and so that will basically lead to 3 quantum numbers. So there's 1 quantum number for each direction. So we assume that we have 3 independent variables. We have the 3 independent spatial directions, x, y, and z, and there's a quantum number to characterize the boundary conditions in each one of those directions. Okay, so just to sort of see how this works, let's consider a 3-dimensional infinite well. So we did the 1D well that we were just discussing, and let's now do the 3D well, and this is going to be much quicker than we did in the 1D case, because basically there's a complete it sort of builds on our understanding of that case. Okay, so here's sort of over here I'm showing a kind of a diagram of the geometry. So you have, again, now we have the three different spatial directions, okay, x, y, and z, and we have a 3D box. Okay, so we have a box that defines our potential. Inside the box, the potential is 0. Outside the box, so at the walls and anything outside the walls, we have an infinite potential. And the box can have, in general, different. It's not necessarily a cube. It can have different length sides. So Lx, Ly, and Lz describe the different directions.